Now consider a situation in very ancient times when people, let's say, when they were living in caves or they were living in small huts, and they needed to make some tools, maybe to make their hut or maybe to make some of the basic tools for farming or for hunting. So what do you think, how they would have made their tools? They would have used, let's say, some stones, some sharp stones, right? And some of the natural wood or any natural substance which is given to them, and by striking them together, right, by using some sharp tools like stone against wood, they would have made some tools. Suppose they need to make a hammer where they need to have some wood part in that hammer. So what they would have done, they would have made that wooden part, they would have carved that wooden part using some stone, right, some pointy stone, and they would have scratched it against it, and they would have collided that stone against that wood in order to give it a particular shape, right? These are some of the traditional ways, some of the conventional ways which we can think of in which those tools would have been made, right? And not only in the ancient times, if you look at some recent past also, some 40-50 years back, you will see that maximum machining that we are doing, whether we are doing turning, milling, or we are doing finishing operations like grinding, you will see that generally what we are doing, we are striking, we are rubbing, we are pushing some hard material, some hard tool against a comparatively soft workpiece, right? So in the ancient time, that wooden part can be considered to be the workpiece, and that stone, the pointy stone, can be considered to be a tool. And using that tool, they scratch, they remove the part of wood to make something out of it. In a similar way, what we are doing in turning or in milling or in, like I said, drilling, grinding, generally what we are doing, we are using a hard tool against a comparatively softer workpiece. I am saying comparatively softer. Workpiece in itself is not soft, but it is comparatively softer than the tool. So we are using a harder tool in order to do more or less the same thing, right? The process of doing may be different. The different setup used for doing this can be different. Obviously, it is different for every operation that I have mentioned. The type of tools are also different, but the basic principle is, you can say, still the same for all these processes, right? All those traditional or conventional fundamentals were still applicable in these processes. That is why these processes are generally called as conventional machining processes or traditional machining processes. But in recent past, many such machining methods have developed and are extensively used in industries which do not rely on this principle. Those machining methods do not require a tool which is harder, which is needed to be pushed or which is needed to be scratched against the workpiece like we do in other machining processes. They have different mechanism in which material removal is done, and tool does not have to be harder than the workpiece, right? So it is fundamentally different from all the traditional or conventional method that we have discussed, and hence these methods are called as, these machining methods are called as non-traditional machining or non-conventional machining. The name is pretty much telling you everything, right? But let's see that what are the exact points where non-traditional machining is deviating from traditional machining. Look, the point number one, I have already told you that in traditional machining, the workpiece is comparatively softer, or you can say tool is harder than the workpiece, but that does not have to be true for non-traditional machining processes. Here, a softer tool also can very perfectly finish a harder workpiece. How? We will see that, because fundamentally it is different. So don't try to understand these principles using the concepts of traditional machining. When you will start reading about non-traditional machining, you will see that totally they are different. The way they are removing material is not the way that traditional machinings do it. That is why you don't have to think now that how these machining processes work. We are anyway going to cover it in this unit. Okay. So the first thing is that when non-conventional machining comes into picture, when workpiece is harder than tool. Okay. Point number 2 is when you need a very good surface finish or a very good accuracy, dimensional accuracy. There also non-traditional machining is better than traditional machining. How? Any process is being done, any machining is done either on lathe machine or on milling machine or a drilling machine. Effectively, what is happening? On microscopic level, if you see what is happening, the tool is actually pushing and entering into the workpiece and removing the material from it. So on microscopic level, there are going to be surface roughness present, right? Surface roughness is going to be there if this is the workpiece and the tool is going inside the whiteboard, let's say. So such kind of lines will be made over it. We have already covered it, right? We already know about it, and in case you don't know, then we have covered it in metrology, right? So surface roughness is going to be there using traditional machining, because ultimately what is happening, it's like if your nails are the tool, so basically you are scratching against the workpiece, right? Even if it looks finished, but ultimately it is a scratch, right? It's a finished scratch, you can say. That is why surface roughness is going to be present in the workpiece which are machined using traditional machining. And if you want to have highly finished surface, even on microscopic level, that is going to be difficult to achieve using traditional methods. At that point, non-traditional machining comes into picture. There are some non-traditional machining methods which can even remove the material on the microscopic level, on the atomic level, at that level. So you can understand the level of surface finish that will be achieved. So whenever a very high surface finish, a high or very high surface finish is required there, or you can also say very high dimensional accuracy. Because in these methods, in these non-traditional methods, in these traditional methods, ultimately you are using a tool. It is fixed on some machine which is running on a motor. There are going to be vibrations, there is going to be shatter. As a result of that, there will be vibrations of the tool. The tool is going to deviate from its defined path. Although that deviation can be minimized to a great extent, but it cannot be nullified. There will be deviations, there will be vibrations, there will be shatter. That is going to affect the dimensional accuracy of the part in the traditional methods. Okay, you have to reduce them. You can do that. I am not saying that all traditional machining methods are bad and they are not used. They are definitely used. There are sophisticated machines there as well. But for some specific cases where you require exceptionally high dimensional accuracy, so you can understand the example that I just gave, where on atomic level the material is being removed. There you can understand what accuracy you will get, right? That is almost impossible to achieve using traditional methods. Hence, when these are the cases, then such methods sound to be better than the traditional ones, right? Similarly, when you have to make a very complex shape, is to be made. Generally, the shapes that we discussed in turning, it was very simple, cylindrical shapes, maybe certain variations in the cylindrical shape, but ultimately the shape was somewhat cylindrical, right? Similarly, in milling or in the drilling, the shapes that we're discussing after machining were comparatively simpler. But when you require a highly complex shape from machining, that is difficult to achieve using the traditional methods. Again, I am not saying it is impossible to achieve. It is possible to achieve, but it will require a lot of effort, lot of sophisticated machines, and obviously a lot of time using traditional methods. At those places, at those applications, non-traditional machining obviously does a better job than the traditional ones. Okay, these are some of the key points regarding non-traditional machining, why they are important, why we are going to study them. This is what you should understand. From the GATE point of view, it is an important topic. You can say that every year one question you can expect in one of the sets. Okay, it's not necessary that you will be having a question from this in your set. It even may be possible that in some year it may not be asked, but you should be prepared for it. At least one question you can expect, and not only numerical questions, theoretical questions are asked from this topic. Generally, if you look at GATE, you realize that a lot of questions are numerical only, right? In manufacturing also, there are many theoretical concepts that can be asked, but generally the focus is on numerical concepts. But in non-traditional machining, major concepts, you can say, or you can say the ratio of theoretical and numerical questions that can be asked is almost 1:1, you can say, equivalent. So theoretical questions also you should be prepared from it, and it's a very easy and interesting topic to cover. So let's first look at the overview of the different types of non-traditional machining processes, and then one by one we will be covering them. So let's start discussing about electric discharge machining. Electric discharge machining, which is shortly written as EDM. Okay, look, in 1940s, some researchers were investigating a way so that they can control or they can reduce the erosion of tungsten, right? You all have heard of tungsten before, I'm sure. It has major application in electrical industries, right? So they were trying to find out some ways so that they can control the erosion of tungsten due to sparking. So whenever some sparking occurs, the tungsten should not erode. So how they can control that erosion, that they were trying to find out by using different ways, different methods. What they found out was that when tungsten was completely submerged in a dielectric fluid, then the erosion was very controlled. They could control the erosion of tungsten due to sparking, electric sparking. When tungsten was immersed, it was surrounded in a dielectric fluid. Now, what is a dielectric fluid? I'm sure some of you know about it already, but those of you who are not aware of that, let me explain them. Look, dielectric fluid is such a fluid which is neither totally insulating nor totally conducting. Means it is a fluid which generally is an insulator. It doesn't allow the electric current to pass through it, but in certain conditions, at certain places, it can get conducting. It can become conducting. How? Look, whenever you have polarity, two different polarities, cathode and anode, and between them, let's say there is a dielectric fluid, okay, and the gap between these two electrodes is not very large, is comparatively small, and you apply a very high voltage across them, okay. These voltages which are present on these electrodes is very high, and the gap between them is very small, and that gap is filled with let's say with a dielectric fluid, okay. So generally dielectric fluids are insulating. It means that the current is not going to pass through them because there is a gap maintained between them, right? If both of them were connected, were in contact, obviously current would have flown. But here there is a gap between them, and between that gap is an insulating fluid, or basically a dielectric fluid, so current will not pass through them. But when you keep on increasing the voltage, a time will come when this fluid medium, this dielectric fluid between them, will break down. It will ionize and let the current pass through this small gap. Basically, passing of current is passing of electrons. So when the voltage across them will become very high and the gap will be very small, electrons will be able, in a such a situation that they can ionize their path, they can jump across that gap, and in that case, what will happen? This path will become conducting. The current will start flowing across this dielectric fluid, right? And that flow of current will only be restricted to this region, right? Not here. Current will not start flowing in random direction. It will be directed. It will be a controlled flow of electrons or controlled flow of electricity. This is the property of a dielectric fluid. What are some examples? Basically, deionized water is a very good and industrially very useful dielectric fluid. From the water, you remove all the ions, right? If you remove all the ions, it will not be in a state to carry on the process of current conduction. But at a certain point, when the voltage will become very high across a small gap, only in that situation it will be able to conduct the current. So deionized water is a good example of that. Is a good example of dielectric fluid. So this is the foundings of the experiment that they did in 1940. So what they were trying to achieve, they were trying to achieve something different. They were trying to look for different ways to prevent the erosion of tungsten. But ultimately what they found, that when such a setup and such an experiment of sparking is carried out in dielectric fluid, in some dielectric fluid, then the erosions are controlled. You can control the erosions, right? And this led to the the formation of machining process, which is called as EDM, electric discharge machining. Basically what is happening in EDM, you can get a pretty much basic idea of that by this thing which I just explained here. Basically what we are going to do, we are going to have sparkings, we are going to have sparks, electric sparks generated to do the machining. Those sparks, I am just explaining this in a very general, in a layman's language. Technical study obviously we are going to do, but as a layman's language, in a general language, what you can consider, that those sparks will hit on the workpiece and they will remove the material from that. How they remove, what kind of sparks are generated, everything we are going to discuss obviously. But consider this setup as a equivalent setup of machining using some tool. When you are having a tool, what you are going to do, you are going to apply a force, you are going to push it, you are going to rub, scratch the workpiece to remove the material. Mechanically it is coming in contact and applying mechanical force to do this. Here what is happening, a spark is being used for that, right? Spark is generated when the two parts are not in contact. So you can say that basically tool is not even contacting the workpiece. Spark is going and doing the job. So a spark can be compared with that situation where the material was being removed mechanically, right? Again, this is a basic explanation just to give you an idea of this. And since there is no rubbing, scratching and pushing against the workpiece, there will be no stress. So basically it is a no stress, or called as stress-free machining. It is a stress-free machining. Stress-free machining does not mean that you won't be having any stress. It means that the stresses generated in the workpiece as a result of machining will be minimal, right, as compared to the traditional machining methods. And due to this spark, this process which is being carried out with the help of electric spark, EDM is also called as spark erosion or spark machining, or it is also called as electro erosion. There are different names for it. There are some more names that we will study when we discuss more about EDM and types of EDM. So this is all about the overview and the background history of this process EDM. Now let's see that how actually we do the machining using EDM. So I have drawn a schematic diagram of EDM here. Let me explain the different parts of this diagram and then we will carry on with understanding the process of EDM. So this thing here is a tool. Okay, it is the tool of EDM. You can see that it has a specific shape, right? This is tool head. Okay, above it. That is not something which is very significant in our discussion right now. This here, which is drawn by blue outline, is the workpiece. This is our workpiece. Okay. You can see that workpiece is connected to the positive terminal, right? So basically the workpiece is anode and the tool, this tool with its tool head, is connected to the negative terminal. So this is cathode, correct? So this is having positive charge, this is having negative charge. Both of them, you can see that they are separated by a small gap, right? They are not in touch with each other. There is a small gap between them. that gap is called a spark gap. Okay, it is mandatory to maintain, and it is not empty. That gap is filled with some fluid. You can see that there is some fluid here, right? It is contained in a box, you can say a setup, inside which there is a fluid, right? This fluid is a dielectric fluid, the same fluid that I told you about a few minutes back. You can also see that there is some lines which I have drawn, which are passing through this tool and tool head and going here. What is that? Look, this dielectric fluid which is present here needs to be circulating. We need to continuously circulate it. Why we do that? I will explain that later. But you need a system, a pumping system, to continuously circulate and pump the dielectric fluid through this setup, through this gap basically. So this passage here passing through the tool and tool head is providing the dielectric fluid directly to that place, to that gap between tool and workpiece. That is ensured by this particular passage. So through this passage, the dielectric fluid directly reaches the spark gap, and then it flushes out, it goes back, it goes out, and using a pump, and we have a filter here, I will explain you the need of filter, it comes back to the spark gap. So these are some of the basic components of this diagram. Now let's see how the process starts. Initially, when you have a certain voltage across the tool and the workpiece, and there is a small gap between them, since dielectric fluid is present which is insulating at that time, no current is going to flow. But as soon as the voltage starts increasing, the electrons start accumulating at the negative and at the tool end, what will happen? A point will come when the material, the medium between the spark gaps becomes conducting, the dielectric breaks down. I have already explained that to you few minutes back. At that time, what will happen? A short period of time, in that short period of time, electrons will flow from negative side to the positive side, from the negative terminal which is tool to the positive terminal which is the workpiece. So you can understand that current is what? Current is nothing but the flow of electrons. When you have high current, means current is nothing but rate of flow of electrons, right? How fastly the electrons are flowing. When we say the current is high, it means that electrons are flowing at a higher speed. So mechanically, if you look at this, what is it? Basically, electrons which were accumulated at the negative end are going to move fastly towards the positive end and strike the positive end, which is the workpiece, for a shorter period of time in a certain region in this dielectric fluid. What is that region? The region is this spark gap. And what is that time? When the voltage built up will be high enough for them to jump. At that time, a controlled spark will be generated. That will be having a particular direction. It is not going to randomly spread, because dielectric fluid here is still insulating. It will not allow the current to flow anywhere. It will just give a low resistance path to the electrons from the negative terminal to the positive terminal across this gap. So if I draw a zoomed in diagram of this region, so this is the positive side, let me draw that here. This is the workpiece, okay, of that region, and this is the tool, and this is the workpiece. So a spark will be generated, and that spark is flow of electrons at a higher pace, which is ultimately going to erode the material and which is ultimately going to remove the material. How it does that? Look, when electrons are flowing at a higher speed, as I was just telling you, that you can look at that flow of current mechanically. Okay, don't look at the current of the flow of electricity or the current electrically, but have a look at it from mechanical aspect. What you will see, that electrons are moving at a very high pace. High current means high flow of high speed of flow of the electrons. Those electrons will be having high kinetic energy, and when electrons having high kinetic energy collide against the workpiece, what will happen? That energy will be converted to thermal energy. The temperature of the workpiece in that localized region is going to rise very high. Although this setup looks simple to you right now, but the temperatures to which the workpiece at this point can reach is as high as 8,000 to 12,000 degrees Celsius. You can understand that what high temperature the workpiece will be reaching in some particular regions, right? Since sparks are very controlled and only at specific point, so whole energy of that spark is going to get concentrated at a certain point. That is why we are able to achieve such a high temperature at a certain point. Obviously, that high temperature has the capacity to melt the workpiece, to melt and evaporate the workpiece, and that is how the material is removed by continuous sparking, by continuous erosion, spark erosions at a very high speed, at a very high frequency in a controlled setup. Forces the material, forces the workpiece to get heated up in that region and vaporize. And this is how the material is removed in EDM. The mechanism of material removal is melting and vaporization due to such spark erosion. So sometimes it is also written as erosion, melting and vaporization. This is the mechanism by which material is getting removed. Recall how material was getting removed in traditional machining methods, right? You can understand that how drastically different mechanism is here to remove the material as compared to the traditional methods. It is here done by spark erosion and melting and vaporization. Okay? And when this material is removed, the removed material needs to get away from the gap, from the spark gap, right? You need to remove that debris from the spark gap, and that is where the role of this pumping system comes. This pumping system pushes the dielectric fluid in this spark gap through this passage, which then flushes out all the material, all the small fine particles which have been vaporized and evaporated from the workpiece away from the spark gap, and then they comes back here in this pump. This is the filter that we have here, which basically filters all the small particles of the removed material from the dielectric, and then this the removed material gets trapped in this filter, and the dielectric, fresh dielectric you can say, again goes through the same cycle. This whole setup, in this whole setup, you can easily see here that whatever is the shape of this die, of this tool, that same shape basically is getting made in the workpiece, because whatever be the shape of the tool above the spark gap, in the same pattern, in the same manner, the material is going to get removed from the workpiece. So that same pattern is going to get replicated on the workpiece as well. And that is why whatever be the shape, how complex the shape is, you can directly make that shape in one go with a very good accuracy. You can see that how materials are getting removed. Surface finish, you can clearly see how high the surface finish is going to be. So in such a manner, you can remove the material and get any shape just by selecting a particular shape of this die, of this tool. Such a process is also called as die sinking. Die sinking. Basically, you are having a die and you are sinking it, and that whatever the die is, the same shape is going to get replicated, right? That is why it is called as a die. In casting, I told you about die casting. So what was happening? Whatever was the shape of die, the same shape was coming in the casting. So in a similar way, this tool here is working as a die. Whatever the shape it has is getting replicated on the workpiece. That is why such a type of EDM is called as die sinking, and generally this is the type of EDM that we do. So EDM is also called as sometimes die sinking. So if you see a term die sinking, just understand that it is talking about the EDM process. Other than this type of EDM, there is one more EDM which is used, is called as wire EDM. Okay, from the point of view of gate, it is not that important, but it is anyway interesting, and obviously some theoretical questions can be asked from wire EDM as well. So let's discuss about that. In case of wire EDM, the tool electrode is basically a wire. It's simply a wire, and this wire is used to do the job of machining from EDM. This wire will be having a certain type of charge, just like the die or the tool in the die sinking was having a particular charge. In a similar way, wire will also have a particular charge, and workpiece will be having the different charge, the opposite charge of the wire. And when they get close and the conditions are made for sparking, the sparking is going to remove the material, as you can see in this animation. And this wire EDM is not only used for cutting and making shapes, but it is also used for creating small holes and small cavities, as you can see in this video. You can clearly understand that if you want to create such small holes or such small cavities using the conventional and traditional methods, it will be very difficult, because if the drilling tool is so thin, it will not be having the enough rigidity to carry on the process of drilling. It will bend, it will break, and ultimately there are going to be problems with the tolerance, problems with the accuracy. But look at this case, how smoothly it is able to cut through and make small holes and small cavities into very hard workpiece as well. So what are the advantages you think we have when you are doing the machining from EDM? The very first one is that it can machine the workpiece of any hardness. Basically, hardness is not even a consideration, right? Whatever is the hardness of workpiece, it is not going to matter, because there is no physical or mechanical medium which is being used to do the machining. So it can machine hard materials easily, as long as they are conducting, right? Because you need to pass the current through it, right? That is why hardness does not matter, but conductivity does matter. The material, the workpiece needs to be conducting if you want to machine it from the EDM. The second advantage is that complex shapes can be machined, right? Have a look at this diagram, these images, to see that how complex shapes also can be easily done using the EDM, which is very difficult and complex to do using the traditional methods. And third is that when we require high accuracy surface finish and we have tight tolerances, there also this is going to work in fantastic way. And this is especially true when the parts are very small. Let's say you have a part which is the size of your nail, and there you want to have complex shape, there you want to have dimensional accuracy and surface finish. Then the problem is definitely going to come if you think you are going to use the milling operation for that, right? There such processes are going to be extremely efficient. Just have a look at these diagrams and videos. The tool in EDM is generally made of copper or brass, and obviously the shape of tool is decided by what shape you want in the workpiece, right? I think you noticed in the diagram that the positive charge was given to the workpiece and negative was given to the tool. Do you think of some reason why we did that, and why in this process positive charge is preferred on workpiece? Because the electrons emit, or they start moving from negative charge to the positive charge, right? We want the hitting of electrons to happen on the workpiece. That is why it is given positive charge, and automatically the tool is given negative charge. Tool is cathode, workpiece is anode, right? But it does not mean that there is going to be no erosion on the tool. Whenever the spark will be there, due to the shock waves, erosion is going to happen on the tool as well, but definitely the erosion of tool is going to be significantly less than the erosion of the workpiece. Okay, so keep this in mind, that tool is not totally safe in EDM. Tool is also going to erode. The material removal which is happening in the EDM is obviously directly proportional to the current, because current is nothing but rate of flow of electrons, right? More fastly the electrons will flow, more will be their kinetic energy, more heat will be generated, and more material will be removed. So MRR, which we write shortly for material removal rate, is directly proportional to the current, and it is indirectly proportional to the melting point of the workpiece. If workpiece has a higher melting point, then the heat generated due to the hitting, due to the erosion of these electrons is not going to will not be able to remove a lot of material. So obviously the melting point of the workpiece is a factor when material removal rate comes into the picture. What do you think are the applications where this EDM can be used? I've already told you a few general applications, that wherever you need difficult shapes to be made or small parts, high dimensional accuracy and all, we have discussed that. But real applications, if you want to know, then they are used in making dies, in making tools and dies. We use different dies in forging, in wire drawing, right? Different dies are used. We have already discussed those. Those are not machined, right? Those are not machined in, generally not machined in some milling or turning operation. They are made using EDM, using these methods, because they are extremely hard. Dies or any such components are extremely hard. So the best possible way to machine them is through these non-traditional methods only. So EDM is used basically in making dies, in cutting dies, in cutting tools, machine tools, in nozzles, right? Because nozzles also need to be very hard. So they are also cut, they are also machined using the EDM. So in such applications, the major process that we use to machine, the non-traditional process, is the EDM. Now whatever be the machining process, whatever be the advantages of the machining process, there will always be some disadvantages, some limitations basically of the machining process, and same is true for EDM as well. The very first limitation of this process is that it can only machine the conducting materials. So even if the material is very soft but it is not conducting, so EDM will not be able to machine it. Point number 2 is that since it heats the workpiece, right? Although the heating is localized, it does not thoroughly or totally heat the workpiece. But in those regions where the material is removed, near those regions the temperature rises very quickly and very high. That changes the metallurgical and mechanical properties of the material. So this is the problem, because basically you are concentrating the energy of current, a high value of current at certain localized points. So that high temperature rise is going to change the properties near the machined surface. That is a disadvantage, a limitation of this process that you have to write in point number 2. That change in mechanical and metallurgical properties due to high temperature achieved near the machined surface. Alright. Third is obviously tool wear. I have already told you about that. Tool wear is something which happens everywhere, right? So same is true for EDM as well, that however the tool wear will be less, but with high current use, at a time will come when the tool is going to get weared, and due to that wear the accuracy will get affected, the accuracy and precision of EDM will get affected, so you have to change the tool. So these are some of the limitations of EDM. Now let's do the numerical analysis of EDM process. In the EDM process, the tool and workpiece which are having different polarities are shown here, and a simplified version of the electrical circuit is also shown, which is used in EDM. This is a resistance capacitance circuit, RC circuit, right? This is the resistor, this is the capacitor, and both of them are variable. They can be changed, their magnitude can be changed. So I am putting up the arrow sign here. The purpose of resistor we already know, that it obstructs the path of current in a simple language. In a similar way, the purpose of capacitance we also know, that it stores the charge, right? Now you can see that the capacitor is connected in parallel to the tool work system, right? So whatever is the DC voltage V naught applied across capacitor, same will be applied across the tool and workpiece as well. But there is a gap between them, the current cannot flow. Across capacitor, what will happen? The charge will keep on accumulating, right? The moment you connected the power source, the voltage source V naught, the charge will start accumulating across capacitor, and same is going to happen across tool and workpiece also, but obviously they cannot store the charge like the capacitor does. So charge will keep on accumulating. The value of voltage across capacitor will keep on increasing because more and more charge is accumulating, and a time will come when there is a spark across tool work due to the breaking of dielectric. So whatever charge has been stored across capacitor, all of that will find a way to flow, right? Right now there is no way to flow those charge to form the circuit, but when tool work will be connected electrically, due to the spark, whatever charge was accumulated will rush through tool work like in the form of current, right? By the flow of electrons. So if we look at the variation with time, this line here is showing the voltage V naught. It is applied across the capacitor, it is applied across the tool and workpiece. As it is connected, it is 0. Initially it is 0, and as the time goes by, this axis is of time, as the time goes by, more and more charge gets accumulated across the capacitor. The voltage across the capacitor keeps on increasing, but up to what point it increases? Up to that point when here the spark occurs. As soon as the spark will occur here, all the charge will pass through that circuit, right? So what is going to happen? For a particular value of voltage, it will increase, and as soon as it reaches that value of voltage, it is going to suddenly decrease. This variation, this is the variation V of the voltage across the capacitor, you can say. And this VD is called as discharge voltage. This VD is discharge voltage. This is that voltage when it is applied across tool workpiece. When it reaches across tool workpiece, the spark occurs. So the value of voltage at which the spark occurs is called as discharge voltage. It is given by VD, and this is how you can represent it on the graph. You can see that the maximum voltage that can be accumulated across the capacitor is same as the discharge voltage VD. After that, the spark occurs and all the charge accumulated will rush through in the form of current. So you can see that suddenly the voltage has dropped. The charge accumulated across capacitor has suddenly reduced because the current has flown. Alright, then as soon as the spark goes off, now again the voltage accumulation across capacitor will start from 0. Again the charge which is given by V naught will keep on accumulating across the capacitor. Same cycle will repeat again. And in many sources you will see that this gap here, this line here, basically you can see that this is T1 charging, this is T2 discharging, right? T1 is showing you the charging time, the time up to which the capacitor was getting charged, and T2 the time when it got discharged, right? So T2 is very small as compared to T1. So generally what we do is we represent it via straight line. We represent this graph in this manner, where T1 is called as TC. TC is the charging time. This we do because T2 is very small as compared to T1. Okay. Now, the expression of discharge voltage is given by Vd is equal to V naught 1 minus e to the power minus T by RC. Vd is discharge voltage, V naught is the voltage applied by the power source. T here is TC basically, charging time. R is resistance of the resistor, because these are variable. So the exact R which is going to be there in this circuit is going to be coming here. C is the capacitance of the capacitor. This is an expression which connects the applied voltage V naught with the discharge voltage Vd. Okay, this is the maximum voltage which can be accumulated across the capacitor. Now in this expression, let's find the value of Tc. Let's find the expression of Tc by rearranging it. So it's going to become Vd by V naught, and this will be e to the power minus Tc by Rc is equal to 1 minus Vd by V naught, which is equal to V naught minus Vd by V naught, and minus Tc by Rc is equal to ln V naught minus Vd divided by V naught, and Rc we can multiply here, Rc multiplied by ln, and minus since we have, so let's multiply it with minus and it will reverse it. So Rc ln V naught divided by V naught minus Vd. This is the expression for charging time. This shows that for how much time the capacitor is going to get charged. So is that of relevance to us right now? No. More relevant is in how much time the next spark is going to happen. This is also told by Tc, right? Because as soon as it goes off, again it takes the time Tc. Correct? Tc. This vertical line is basically showing the spark, right? When all the voltages of across capacitor is suddenly coming down. Why? Because all of the charge is rushing through this circuit, through the tool work circuit, right? So in this time, if this is a spark, so after Tc time, next spark will occur. So in a way, Tc is telling you that after how much time the next spark is going to occur. And if you take its reciprocal, then it is going to tell you the frequency of spark, right? If you do 1 by Tc, then it will tell you that in 1 second per second how many sparks are going to happen. That is given by 1 by Tc. You just have to take the reciprocal of it, right? Now let me rub it off and tell you something more. Now whatever is the energy of the spark between tool and work, all that energy is coming from whatever charge was accumulated across capacitor, right? So how much is the work potential of that charge which is accumulated by the capacitor is same as the energy released per spark, right? Whatever is the work potential of the charge stored is same as the energy of the spark, right? So if you want to know how much energy is released per spark in any form, so energy released per spark is equal to work potential of the charge accumulated across capacitor, and that is equal to half CV square. But what you will take the value of V, which is the potential difference across the capacitor when the spark is occurring. So when the spark is occurring, just an instant before that, the voltage across the capacitor is Vd, right? Just when the spark is occurring, before that it has reached the value of Vd. So this V is equal to Vd. Direct question has been asked in GATE from this expression. Okay. If I want to know the energy of spark per unit time per second, so how can I know that? If this is E, energy of spark, of a single spark, then you have to multiply it with F, with number of sparks per unit time, right? We already know the expression of F. This is equal to 1 by Tc. We already know the expression for Tc. So you can calculate that how much energy is being released by the sparks per second. If you want to know the material removal rate, this expression is given by E multiplied by F divided by specific energy. Specific energy tells that how much energy is required. Let's talk about units. So how much energy is required to remove unit volume of material from the workpiece. And in the numerator, what do you have? You have energy released per second, per unit time. So if you put both of them, joule will get cancelled, mm cube will come on the top. Ultimately, you will get the units in mm cube per second, right? It's a general tip. Whenever you get a question from MRR, because MRR is such a thing which we have seen in traditional machining as well, and you will see in non-traditional machining as well. Okay. So across these processes or any of the process where MRR is to be calculated, and suppose you are not aware of the concept or the expression of MRR, just use the basic concepts and try to get the units right. Ultimately, unit should be volume divided by time. Use some logic, some basic logic. Logic means basic aptitude, and this funda of matching the units. Ultimately, you will get the required expression for the MRR. Here, what we are doing, let me tell you. The numerator here is telling you that how much energy is released per unit time, correct? That I have already done. And denominator is telling you that how much energy is required to remove unit material. If you divide both of them, you will see that you will ultimately get the units of MRR. So in this way, you can learn it. In some of the questions, you can get directly a constant K, where K is nothing but 1 divided by the specific energy, which is going to be having the units of mm cube per joule. So per joule, how much volume is being removed? If that is given, so you simply have to put it here. That is nothing but 1 divided by specific energy. Although no question has been asked in GATE yet from the MRR of EDM. And in general, the only expression that is going to be of use for you is this one. Rest, the expression that I told initially of charging time and all, and this expression, no question has been asked in GATE yet from these expressions, but it is very much in the syllabus and you must be knowing that it's not that difficult, right? Basic expressions you have to use, basic concepts of electrical engineering you have to apply, and you will be able to get the expressions. Now let's have a look at the variation of MRR with the different operating parameters of EDM. Operating parameters of EDM means resistance, capacitance, current, the gap between the tool and workpiece. These are some of the things that you need to decide before carrying out the process of EDM, right? So these are the operating parameters. So how variation in these parameters is going to affect the MRR qualitatively, let's have a look at that. The first variation is between resistance and MRR. So if the resistance of the resistance in the circuit, if that resistance increases, the value of current will decrease. If the value of current will decrease, automatically MRR is going to decrease, right? I've already told you that how material is removed by the flow of electron, right? Those electrons which hit with high speed against the workpiece, ultimately they generate the thermal energy to melt and evaporate it. So if the current will be less, the rate of flow of electrons will be less, so automatically less material will be removed. So this is how the variation occurs. If you increase the resistance, current goes down, MRR goes down. Coming to this, obviously if you increase the value of current, MRR is going to increase. In a similar way, if capacitance increases, means the ability of the capacitor to hold the charge, more energy increases, right? So if C increases, from the expression also you can recall that energy per spark will increase. Half CV square is going to increase. More energy will be there, more heat will be generated ultimately in the workpiece, more material will be removed. So this also has a variation like this. Increase the capacitance, MRR increases. Coming to the spark gap, this is where it gets interesting. Look, if the spark gap between tool and workpiece is less, what will happen? It will not require the buildup of a high discharge voltage. The value of VD will be less because it has to jump across a very small gap, right? Consider a scenario when they are very close, almost in contact with each other. Then it's easiest for the current to flow, right? VD will be very less if they are in contact. In a similar way, let's say they are not in contact but very close to each other. So what will happen? The value of VD required to jump across the small gap will be less. So the value of VD will go down. Okay. So from this you can think that okay, if V is decreasing, so ultimately in half CVD square, the energy per spark half CVD square, this will go down. So total energy release per spark will decrease. So MRR will be less. This you might think. But there is one additional factor here, that is the frequency of spark. Look, if VD is less, what will happen? In the variation of V versus T that I showed you, quickly it is going to get discharged. TC will also reduce, right? Because TC is the time it took for the circuit to build up VD across capacitor. If VD will be less, time of charging will be less. So what will happen? Frequent sparking will be there. It needs not to reach a very high value of VD, but only a smaller value of VD. So suddenly it will, the spark will occur, and next will also start, the next spark. So if VD will be less, number of sparks per unit time are going to increase, because it will take less time to reach VD. So two factors are there. VD is less, but more number of sparks are there. Or in other words, the energy per spark is less, but there are more number of sparks. Now, in such case, both of them combined are going to decide what is going to be the variation. If the value of VD is very less, it means that the energy per spark will be very less. So even though the frequency is high, the MRR is not going to increase. Okay. And also at the extreme point. At the extreme point means when the spark gap is very high. So if the gap will be very large, the value of VD will be very high, because in order to jump across a large gap, more potential difference is required, right? So VD will be high. But again, since VD will be high, so it will keep on charging for a longer time, and then the spark will happen. So frequency will fall again. So in one case, the energy per spark is very less. In other case, the frequency is very less. So both these situations are not ideal. The ideal situation is going to fall between them. This is telling you the optimum gap. Whenever you have two such factors which are working against each other, so too less or too extreme of it is not going to be a good thing. Good thing will be to have a value, optimal value lying between both of them. So this is how the variation of spark gap of MRR is going to happen with spark gap. Again, I am telling you, GATE has not asked question on variation of MRR with the operating parameters of EDM, but still all of these are highly relevant concepts for GATE. So don't ignore them considering irrelevant. It is very likely that GATE can ask you questions from them any year. Okay.